Yes, Prof.
Okay, record. Okay, let me just start today. I'm sharing the whole screen, so I'm not sure if you can see this. Can you see this file?
Yes, Prof.
Yes, Prof. Yes.
Okay. So this is a typical file for everyone doing numerical combustion, and you probably recognize this. So it's a text file that is used in the so-called Chemkin environment. Chemkin is a set of programs that were released long ago, and then they were modified. And they're similar to Cantera. Cantera is sort of a newer approach. This was written in Fortran. Cantera is more Python kind of platform. You can, by the way, go to the Cantera.org page and have a look. It's quite, now that we're beginning to do some of both equilibrium and kinetic examples, you'll recognize some of the things that you can do. This was like an older approach, still very valid, and it was an input file for this program. And what it is essentially your chemical kinetic mechanism. So you see here the list of species. This is a very small mechanism. It is a reduced mechanism for CH4. So CH4, you will recognize CH4 as being the most complex hydrocarbon here. Of course, it's the simplest hydrocarbon that exists. You can see that we have a bunch of intermediate species that come from the breakup of CH4. So you can see, for example, CH3, and so on. And then the final products that are H2O and CO2, and then some intermediates which are related essentially to the reaction of oxygen atoms. You see that oxygen will break up itself into oxygen, atomic oxygen, and then will react as, for example, this radical OH, okay, with the hydrogen breakup of the fuel molecule. So you have a bunch of species. In this case, it's about 16 species. You also have a dilutant like nitrogen. There is no nitrogen chemistry here because it's a simplified chemistry. But in reality, you do have a nitrogen chemistry. And you see that this is the list of all possible elementary reactions. Okay? So it says here reactions. And you will recognize that they're, most of them, okay, are essentially bimolecular, okay, involving two molecules on the left and on the right. You may notice that some of them have an M, okay, and that's exactly what we mean by what we said, okay, it's a third body. So these reactions, generally speaking, will be subject to a reaction rate that is a little bit more complex than the pure Arrhenius form that we've seen, and it's pressure dependent, okay? Look at these three columns here, okay? If you remember what we said yesterday about the three columns, the three parameters, B, alpha, and the activation energy, these are the only three numbers that you need Can you please be a little bit more on time next time? Thank you. To determine the reaction rate. Okay, and that's exactly what this file will tell you, will give the program. Okay, the first column is the pre-exponential factor. The second column is the exponent of the temperature. And the third column is the activation energy. Okay, these are in some units that I won't even tell you, but it's CGS units, so they will be given in centimeters and in ergs and things like that, but you can convert them very easily. Okay, so you can imagine far more complex scenarios where you have thousands and thousands of reactions. I won't show you these files, but you can imagine how complex they are. Another thing you may have noticed, you only have 3 numbers, but the reactions are reversible. So in fact, I don't just need the forward reaction constant Kf, okay? But I also need the backward reaction constant Kb, right? Remember? So these 3 numbers are in fact relative to, so these 3 numbers will give us the K forward. It will give us essentially only the forward process, so the reaction constant of the forward reaction. The reason why we're not given the backward reaction is that the backward reaction constant must be in full agreement with the equilibrium constant. If you remember, the ratio of the forward and backward reaction rates must be equal to the essentially to the equilibrium constant. That's what we said. So you can't specify both, because clearly then you run the risk of not being coherent with the thermodynamics, with actually the equilibrium constant. So we will derive K backwards, okay, from the K forward and the equilibrium constant. Okay, that's essentially the bottom line here. Let me try and share the whole thing. Okay. Okay, can you see the whiteboard? Can you see it?
Sì, professore.
Okay. Very good. So let's go forward. We had talked about this visualization, which I think is very useful. Okay, when you think of both a representation in terms of equilibrium and in terms of kinetics, always think of this as a sort of a energetic pathway. Okay, and the fact that in reaction, well, in chemical kinetics, you must really go over this energetic bump, which represents the activation energy, whether it's an exothermic or an endothermic reaction. Okay. Well, another thing that we can say here is that, well, suppose that the temperature exponent is 0, and suppose that B is a constant. The reaction constant here will simply be very, very simply some constant times the exponent of minus EA over RT, right? So the way in which B, okay, and EA can be determined once you accept the fact that they have to have this sort of functional form is, well, you can take the natural logarithm and you will have something like this. And so essentially, if you know the reaction rate and you can measure it, for example, experimentally, then you can correlate essentially the experimental data, okay? And you will have a series of, let's say, of points here. And because this is a line this would be logarithm of K, okay? You simply do a line fitting with this particular functional form, and you will see essentially that the intercept here will be logarithm of B, and the slope essentially, okay, of this thing would be minus EA over RT, okay? But that's just an obvious thing. More importantly is to understand is the role of the activation energy, okay? what role does it play in chemical kinetics? Why is it so important? Usually, of course, I mean, combustion in general is a wide subject, okay? And it is prone to many sort of analyses, from numerical to theoretical to something that is called asymptotic analysis. And the reason why it's so vast, okay, the application of asymptotic analysis, is because the activation energy is in generally very, very large. And when you have a theory, okay, where you can extract parameters that are very large in general or very small, okay, you can do some sort of approximation, okay? You can have these parameters, for example, small parameters, you can tend it to 0, okay, and see what happens, okay? And, well, the ensuing simplification that you get will reveal many of the hidden aspect of the otherwise very complicated nonlinear aspect of the theory, okay? This is the very sort of short way of saying this. Let's see why, and so you can say that a large chunk of the asymptotic theory is called high activation energy, okay, theory, or high activation energy assumption. Let's see why in a form for the reaction, the Arrhenius reaction, which we simplify to the extreme. So we always think of alpha equals 0, just for the sake of simplicity, and B could even be A or something, okay? It's just a constant. And then the exponential of, and we leave clearly this exponential form, which is the most crucial part. Let us analyze this functional form. Why is it so important in combustion, and what are its ramification or consequences, okay? Now, first of all, there are many definitions that you can introduce. One is the activation temperature. It's just totally equivalent to the activation energy. So the only thing is that it's measured in Kelvin. So you have the activation energy divided by R, okay? So in terms of units, you will have the activation energy is joules per kilogram, and R is given in joule per kilogram per Kelvin. So this is ends up being measured in Kelvin, okay? And so you can write essentially the reaction constant as A in the exponential of a minus TA over T, okay, where T is your current temperature, okay? And again, always remember what this means, okay? It is always the fraction of collisions that have an energy which is bigger or equal to the activation energy, EA, okay? Combustion is a theory that has a bunch of also non-dimensional numbers. One of the most important ones is the Arrhenius number, which we call AR, okay? And it's essentially a measure of how large the activation energy is. So if this is the activation energy, we normalize it by another energy, which is the universal gas constant times the maximum possible temperature that you can have in your system. Clearly, this is also written as the activation temperature divided by Tmax. Now, what is Tmax? Well, generally speaking, the largest possible temperature that you can encounter in your system is the adiabatic flame temperature, okay? Okay, so in a stoichiometric combustion of a hydrocarbon, you will have in air around a little bit more than 2000 Kelvin. In pure oxygen, you can get up to 3600 Kelvin, okay? Not more than that. Okay? So that's a measure of the maximum possible expression, okay, of the temperature. So Arrhenius, okay, can be thought of a ratio of the activation energy divided by essentially the maximum thermal energy in the flow, okay? Now, we don't know whether this Arrhenius number is actually bigger or smaller than 1 at this point, okay? But what we know is the activation energy that is typical for combustion reactions is between, let's say, 20 and 60 kilocalories per mole. Okay? So about 20 to 60 times 10 to the 3 calories per mole, okay, where 1 calorie is roughly 4.18 joules, okay? And okay, these are numbers, okay? Tmax, well, what's Tmax? Again, it's the maximum possible temperature that you can have in your system, in your chemical system or combustion system. Now, in order to estimate Arrhenius, we can say that it's anywhere between 500 Kelvin, a very, very, very cold combustion, let's say, all the way down to, let's say, 3,000 Kelvin, okay? Not more than that, okay? So with these numbers, okay, with these ranges, we can actually estimate what the minimum and maximum Arrhenius number is, okay? Well, we have to remember that R is 8.314 joule per Kelvin per mole, okay? And so we can stick all these numbers in the Arrhenius definition, okay? So remember, Arrhenius definition is EA over RT max. So what's the minimum possible Arrhenius? Well, at the denominator, okay, well, R is R, then you can plug in this number. At the denominator, we will plug in clearly the maximum possible temperature that we have envisaged for the system, so 3,000, and on top, we just plug in, so that's the conversion. We plug in clearly the minimum, okay? Activation energy was just 220 times 10 to the 3 calories per mole, and then times the conversion. Okay, and we get something of the order of 4 or 5. Okay, so the minimum Arrhenius number is actually bigger than 1. What about the maximum? Well, what we have to do now is plug in the minimum temperature at the denominator, and then the maximum at the top, and we get something of the order of 60. Okay? So we can conclude that the order of magnitude, okay, for this Arrhenius is about 10, okay? So generally speaking, we conclude that the Arrhenius number for combustion reactions is a number that is generally much bigger than 1. And that is something that is always true, okay? So the activation energy, okay, is which is essentially the energy that must be a larger number than the average sort of thermal energy that you have in your system. okay? But mathematically, it means something very important, okay? Well, it means essentially that the exponential, okay, which we can write as this number here, is essentially a very, so that also means that TA is very large, okay? It means that this factor here is very sensitive to variations in temperature. I hope you agree, because clearly the factor multiplying or actually on top of 1 over t, or multiplying 1 over t, is extremely large, okay? So that means that if the temperature varies varies just a little amount, this factor here will vary substantially, okay? Now, what does that mean in terms of the reaction rate, okay? Well, one thing that we can do is we can consider the maximum reaction rate attainable. What's the maximum reaction rate that we can attain? Well, it will be a measure, okay? Forget all the constants, okay? And forget the particular reaction. It's clearly attainable at the maximum temperature. So it will be T minus e to the minus TA divided by T max, okay? That's an expression for the maximum reaction rate that we can attain, okay? Irrespective of the reaction and of the constants that will appear in the front. So what we can do is non-dimensionalize the factor e to the minus TA over t with respect to the maximum possible value, okay? So this fraction here will vary from 0 to 1, okay? So 1 means essentially that the temperature is such that it's T max, so we've attained the maximum possible reaction rate, or T can tend to very small values, and so the reaction rate is almost 0, okay? Well, this is an easy to express. This will be the exponential of minus TA over T. Minus is a plus, so TA over T max, okay? You can take the TA over T max out, and this multiplies 1 minus T max over TA. Okay, this is very simple. And essentially, you end up having, well, TA over T max is the Arrhenius number, 1 minus T max over T. Okay, I can actually between essentially, well, as a function of, let's say, T over T max, okay? So it will get to the maximum point, which is 1, clearly, when T is the maximum possible temperature. And what we have here is the fraction of the reaction rate constant with respect to the maximum possible reaction rate. So even here, we will have a plateau here at 1, obviously. 1 means it's the maximum possible, maximum reaction rate. Okay? Now, clearly, Arrhenius now is a parameter. So if you try and graph this, okay, you have functions which are essentially like this, okay? So as the temperature increases and approaches the maximum temperature, okay, the reaction rate clearly increases, okay? And then it will reach a maximum, okay, of 1, okay, maximum possible, exactly at the maximum possible temperature, obviously. Now, the interesting fact, it's not so much that the reaction rate increases with temperature, this we know, okay? We're essentially having more and more, larger and larger fraction of molecules individually having energies bigger than the activation energy, okay? What's interesting is the sensitivity of this function to the Arrhenius number, okay? We have essentially a situation where as the Arrhenius number increases, okay? So this arrow represents essentially the increase of Arrhenius number. As the Arrhenius number increases, you see what happens. A very important thing happens. Okay, suppose that this is Arrhenius 1, this is Arrhenius 5, and this is Arrhenius 50. Okay, now we said that the Arrhenius number is more of the order of 10, if not more. Okay, so it's a combustion reaction is more has more of this behavior. Okay, now what does this behavior tell us? For Arrhenius numbers, so I activation energies, is that essentially the reaction rate, look at this, is essentially inhibited or suppressed for most of the temperature range. So as you increase the temperature, the reaction rate almost doesn't increase. Okay? It's very, very, very small increase. And then, essentially very close to the maximum temperature, only then, okay, you have essentially a full release, okay, of the reaction rate from, let's say, almost 0 to its maximum value, okay, in a very narrow range. So for most of the temperature range, because the activation energy is so high, for most of the temperature range, the reaction rate is suppressed. Okay, it's almost 0. Nothing happens. And this is really a crucial property of combustion reactions. You can still hear me, right?
Yes, Prof.
It's a crucial why is it a crucial property of combustion reactions? Well, so shall we write it? So high EA, so high Arrhenius, means, okay, reaction rate suppressed until T is very close to Tmax, okay? Now, why is it important? Well, it's important because this particular property is the cause of the fact that combustion reactions are fast, okay? Remember, we said a piece of metal will rust in years, okay? Combustion will take place in fractions of a second, okay? Or it's a part of the story. Then we'll see that there are more reasons why the combustion processes are very fast, okay? This is also something that we'll see at the end of the course, which is flames, okay? Which are more of like a fluid dynamic solution of combustion, okay? Or combustion waves. Well, flames are very thin, okay? So these two facts, okay? The reason for this, essentially, okay, is that the combustion reactions are, generally speaking, high activation energy reactions, okay? So they end up having a reaction rate that's very, very sensitive to variations in temperature, okay? Now, let's see if we can sort of understand this graphically, okay? Suppose that, okay, I talked about combustion reactions being fast. So there is a concept of time and time evolution, or flames being very thin. So there is a concept of spatial evolution, so evolution in space, okay? So suppose that you have, you're monitoring, okay, along either time or along a direction x, okay? You're monitoring two things, okay? Suppose that you have the concentration of a species going to a product, okay? So you're monitoring, okay, the concentration of C. You start from, so you have a reaction, an irreversible reaction. So you can think of C as being the fuel, okay, burning up and being depleted. So you start from an initial concentration, and you will have now, obviously, a decrease. Now, I don't know how this decreases. We would have to solve the equations, right? The conservation of species equations. So I would have to write my system of ordinary differential equations, and I would also have to monitor the temperature. So let's follow the temperature as well, okay? We start from an initial temperature T0, okay? And we reach Tmax, okay? Why does it increase? Well, we know that the reactions are overall exothermic. So in a situation where I'm not exchanging heat with the surroundings, so in an adiabatic sense, okay, the temperature will increase, okay? Now, obviously, the fact that I'm doing these linear is meaningless, okay? They're not linear. Okay, I would have to solve at least, to the very least, the system of ordinary differential equations for temperature and for species, okay? For a flame, it's even more complicated. I would have to solve a one-dimensional problem of fluid dynamics, okay? Where on top of the reactions, I should also include transport phenomena. And by transport phenomena, I mean essentially convection and diffusion, okay, of both mass and energy, so temperature in general, okay? So I would have to write down a conservation of equation for all the species and the temperature, okay, which include terms of convection and diffusion transport. So we will see that in time. But because it's a qualitative, let's say, analysis, well, I will just tell you that the species, the reactant will decrease, okay, in concentration, and the temperature will increase in concentration. Now, let me see if I can say something about the reaction rate, okay? So again, it could be along T or along even X, okay? Obviously, in time, you would have a transient evolution, okay, with no space, okay? So a spatially homogeneous transient evolution. In space, you have a steady state evolution, okay, along a direction. So you have a stabilized flame, okay? Well, we know that the reaction rate is equal to essentially, well, look at this reaction over here, a concentration times a reaction constant. So A e to the minus EA over RT. That's what my reaction rate is, okay? So if we start from here, okay, well, what's going on with this function? Well, it has two parts, right? Well, C is decreasing, but T is increasing. So at the beginning, this will, because it's an exponential, it will dominate. And so we will start increasing the reaction rate, okay? But then look at what happens to C. It decreases, so eventually, and it goes to 0. So eventually, the reaction rate is going to be completely suppressed, okay? So this is what you have, for example, in terms of the evolution of, say, a species when you reacted in a reactor, for example. It's what you can see by monitoring along a flame, okay? You can see the reaction rate, for example. It will increase and then decrease. And actually where the flame actually is located, okay, in space is exactly the volume or the area where the reaction rate omega is non-zero. Okay, so around here. Now, I drew this for quite a small activation energy. What happens with the activation when the activation energy is extremely high? Well, you will have something like this. Okay, so again, this is the activation energy increasing from here to here, okay? And so you see that this zone, okay, for realistic, very high values of the activation energy, this zone, which can be the reaction time, or, okay, the flame thickness, is extremely short. Okay. Now, clearly, this was a qualitative approach. Okay, which doesn't make any sense quantitatively because we would have to. We are assuming a general sort of decreasing and increasing behavior for clearly the reactant and temperature, which of course will happen. In reality, these will not be linear. Okay, these will be nonlinear. But again, qualitatively, I just want to show you what the role of the activation energy is. Okay, if you have two profiles, okay, if you increase the activation energy, generally speaking, the reaction rate will be inhibited unless or up to a very thin layer where it will release all of its reaction rate. Okay. And so when you're talking about an homogeneous reaction, okay, in a reactor, the reaction will be very fast, okay, in this small time. If you're looking at a flame, the flame will be thin, okay? Now, other factors will intervene in a flame, of course, like diffusivity and things like this. But generally speaking, the chunk of the phenomenon is eaten up by this reaction rate. It's played, most of the role is played by the main actor, let's say, is the reaction rate. Okay? Now, oh, and clearly, well, yeah, I told you why it's increasing and decreasing, right? Because eventually C is 0. Now, we can start playing around a little bit with essentially two prototypes of reactions, okay? Just to see now how the temporal evolution plays out. Now, we will talk about reversible reactions. When we have things like these. So as a prototype kind of reaction, you have a forward and a backward rate, okay? And then A and B. Now, the interest in this essentially is that each of those steps that I showed you in the Kempkin file, okay, in a combustion reaction will be reversible, okay, of this kind. The interest in analyzing these systems here is I'd like to see, for example, whether there is a link with equilibrium. We've seen that there is a link with equilibrium, obviously. and the fact that if Kf and Kb is one bigger than the other, if eventually the shift of the equilibrium will be to the right or to the left, okay? So we're doing sort of an analog of, let's say, the equilibrium shift, okay, that we saw with the equilibrium constant, if you remember. Now we're doing it dynamically. We want to see in time whether after some time, so asymptotically, this reaction will shift its equilibrium more to the left and to the right as a function of how large these coefficients, these reaction rates are. Now, another paradigmatic reaction or reaction mechanism is what we call consecutive reactions, which is more, let's say, which is closer to an idea of what combustion actually is. By consecutive, I mean we start from an initial species, which you can think of being the fuel or the reactant, and this will react irreversibly, okay, through a reaction of this kind, K1, okay, to form B, okay? And why is it consecutive? Because then this B, okay, will itself react and be depleted through a reaction K2, okay, to form the final product. So you see that essentially the second reaction cannot happen without the first reaction, because you have this special species here which has a particular role which we call the role of the intermediate species, okay? This is very typical in combustion reactions, because you start from a fuel, okay, and you end up having essentially products like H2O and CO2, okay, very stable products at the end of your oxidation, essentially reactions where essentially carbon has been oxidized to O2, and obviously oxygen has been reduced. But you see that it doesn't happen directly. A does not go to C directly. But what happens is A will decompose, essentially, okay? So there is a bunch of, let's say, either decomposition reactions, okay, where the bigger molecule break up, okay? And they will form these species B. Now, obviously, this is a hyper simplification of what the actual mechanism is. I mean, I showed you what the mechanism is. It's very complicated. But it is true that in general, in combustion, you have intermediate species, which generally speaking are called radicals, essentially, or free radicals, essentially because they are extremely reactive species that are only transient, okay, within the evolution of the combustion process, and they will have free electrons, so available covalent bonds, so they're very reactive. They will try and react with a lot of stuff. It's the reason why when you smoke, it's really bad for you, because you're inhaling a lot of intermediate species of combustion, which is very reactive. Of course, they will react with what? With your body, okay, with your lungs. And so by smoking, you are actually burning your lungs essentially very slowly, okay, through over the years. So I don't suggest you smoke. Usually the creation of this intermediate species is also called radical pool, meaning that in order for your final products to form, you first need to form a pool or a group of radicals, okay? So a big chunk of radicals. And then they can eventually slowly, if you will, more slowly, be oxidized towards your final products. Okay, so these are the two paradigmatic equations. We're going to look at them next time individually, okay, and try to start working with the individual reactions and see if we can derive some mathematical techniques, okay, with which we can categorize, especially the fact that we're going to be dealing with different reaction rates and therefore different time scales. This is what I've already told you last time. The fact that these constants here can be very different between each other will translate in the existence of multiple timescales. In this particular case, for example, you will have the creation, for example, of a radical pool very fast if K1 is large, and then the oxidation or the consumption of the radical pool B towards your final product C in a slower manner if K2 is small. Is there some mathematical technique that we can think of that can help us characterize the evolution of these species? Okay. Okay, very good. So with this, I will stop it here if there's any questions.
Scusi, professore.
Sì. Sì.
Io ho un piccolo chiarimento. Diciamo, la forma di Arrhenius della costante di reazione, chiaramente dal punto di vista teorico, trattando della teoria delle collisioni, si applica a reazioni elementari, ma diciamo, generalizzando, per anche un processo globale, la K, trattando un processo globale, si usa una forma di Arrhenius.
Ottima domanda. Si usa la stessa forma, tipicamente, di Arrhenius, ma con costanti alfa A, quindi pre-exponential factor, esponente di T, energia di attivazione e ordini di reazione, attenzione, quindi gli esponenti che vanno sulla concentrazione molare, che sono tipicamente dei numeri di fitting, cioè dei numeri che sono stati in qualche modo aggiustati in modo tale da farsi tornare le cose. Ok? Quindi non hanno nessun rapporto con la realtà collisionale, proprio perché quella equazione globale non rappresenta un processo collisionale, ma rappresenta, se volete, il combinato disposto di tantissimi processi collisionali, e quello in qualche modo è il risultato finale. Okay? Spesso e volentieri non conterrà tutte le scale, per esempio, più veloci, che sono espressione, dovendo ovviamente andare a prendere tutto il processo di combustione, dovrà stare attento più che altro a riprodurre soprattutto correttamente i prodotti, no? Quindi di ossidazione, facendo molta meno attenzione ai prodotti intermedi. Ecco perché tutte le scale tipicamente veloci, che sono connesse con i processi collisionali che hanno a che fare con i radicali, quindi con i processi appunto con gli intermedi che sono veloci, verranno perse. Okay? Quindi sono sostanzialmente dei numeri di fit. Se volete poi ve lo faccio vedere, ci sono addirittura delle ossidazioni di alcuni idrocarburi che sono rappresentabili sostanzialmente, la cinetica stessa è rappresentabile sostanzialmente con un'equazione sola. Ovviamente l'accuratezza è scarsissima rispetto a risolvere tutte le equazioni elementari. Ok?
Ok, grazie mille. Arrivederci.
Arrivederci a tutti.